Everyone, my name is Germán Gerardo Sánchez Hernández. I'm from Mexico. I am a master student at Instituto Politécnico Nacional, conducting research at the Optomechatronics and Energy Laboratory of UPI. And today I'm going to present my work entitled Sequential Acquisition of Laser Pulse using Oscilloscope Control through Python. The presentation is organized into a 7 sections. In the first, the introduction, then methods, experimentation, results and discussion, conclusions, future work, and reference. According to the World Health Organization, the most common types of cancer are lung, colorectal, liver, breast, and stomach cancer. In 2023, around 800,000 deaths were registered in Mexico. 11% were due to malignant tumors. Therefore, it is essential to develop diagnostic alternatives that are faster, safer, and less invasive to improve early detection. The fluorescence is a method used for a diagnosis of different pathologies like cancer. The animation shows the fluorescence process. We have a fluorophore. That's uh, that fluorophore absorbs light and becomes excited from the ground state, that is zero, to a higher energy state or high energy level. Uh, this is S1 or S2. After a short relaxation, it's returned to the ground state by emitting light. This emitting light is a fluorescence, which occurs at the timescale of nanoseconds. The lifetime of this phenomenon is very short. The fluorescence lifetime refers to average time a fluorophore remains in its excited state before emitting a photon. The objective in this work is extract lifetime like those of. On the left side, we have the exogenous fluorophores, which are artificially added in laboratory tests and experiments. Among them is rhodamine B, rhodamine 6E, and fluorescein. On the right side, we have the endogenous fluorophores, naturally present in biological tissues and used for cancer diagnosis, like FID. Both types share the characteristic of having short lifetimes, less than 5 nanoseconds. Therefore, it is expected that the instrumentation will be available or able to extract such short lifetime for hair-related applications. The main components employed in the instrumentation were obtained from the Thor Lifetime Resolve Absorption Spectroscopy Kit, the EduTRAS 1. Um, it is a Thracian absorption kit from which the main components were used. First, the laser module NPL45B included in the kit emits a wavelength for 450 nanometers and generate pulse with from 5 to 39 nanoseconds. Then the photodiode, PDA36A2, with a bandwidth of 12 MHz, with a measurement wavelength range of 400 to 1100 nanometers and maximum optical power of 10 milliwatts. And finally, the data acquisition and control board, the National Instrument USB 6341, with a 10 MHz of bandwidth and 500 kilosamples per second sampling rate. We have the instrumentation. This diagram shows the instrumentation setup. The control card drives the 450 nanometers laser, whose beam is particularly reflected by a slide to reduce the intensity. to about 4%. The photodiode captured the signal which is sent to the oscilloscope and then processed by the computer. Uh, a key-side oscilloscope was added to the setup because the acquisition board didn't provide sufficient bandwidth or sampling rate for the measurements. This oscilloscope has a bandwidth of 200 MHz and sampling rate of 2 gigasamples per second. Well, the sequential equivalent time sampling technique um, um, consists of taking one sampling at different point in time during each repetition of the signal. After many repetitions, these samples are combined to reconstruct the complete waveform. In the image, each laser pulse repetition is sampled at a slightly different delay in time. By shifting the sampling point by step, all the pieces of the waveform are collected. Once combined, these points reconstruct the full signal. This approach makes it possible to overcome the limitation of real-time acquisition, acquisition and analyze fast optical phenomena using the available instrumentation. Well, the Python code, the function, is explained in this flowchart, where it begins with a connection between the oscilloscope and the control board through the VISA protocol. Then defines the acquisition parameters such a number of sample total points and the time interval between them. Once the laser is turned on, the program acquires a data point every uh, zero point 0.2 nanoseconds for each pulse until the full signal is reconstructed. Finally, all data are saved in a .csv file for further analysis, including FWHM calculation. For the experimentation, two tests were performed to measure the pulse width of the laser module. The first um, test correspond to a pulse width of 5 nanoseconds, and the second to the 39 nanoseconds. The data acquisition parameters for both tests were 100 samples per point, 2500 points for each measurements, the time interval of zero point 0.2 nanoseconds between each point, and the laser frequency of 200 Hz with an optical power of 30 milliwatts at output. But after of slide the power reduced to 4%, approximately 1.2 milliwatts at photodiode input. For results and discussion, the figure 8 presents the results of the first test. The plot displays good definition to the high number of accurate data points. However, considering that the laser module was set to a pulse width of 5 nanoseconds and the measurements FWHM is approximately 29 nanoseconds, this indicates that the instrumental response is slow and stretches the pulse due to the photodiode. This is caused by the bandwidth of photodiode as shown in equation 1. The rise time is determined by the bandwidth, which in modeled use a first order RC circuit. Uh, for the next test in figure 6, it's possible to observe a measurement value much closer to the setting on the model since the FWHM is approximately 42 nanoseconds, which is significantly better than in the previous test, considering the slow response of the photodiode. Um, this technique reduces the need for a high real-time sampling rate to reconstruct repetitive signals, relying in this case on zero point 0.2 nanosecond steps between points. The main limitation of this configuration is the photodetector uh, rise time, which for 12 MHz is about 29 nanoseconds, defining the instrumental response and broadening the pulse. Um, in conclusion, according to the test performed, the instrumentation system developed is limited by the slow response of photodiode. Considering that the semiconductor properties don't allow for a faster response and higher configuration bandwidth is 12 MHz. Therefore, it was not possible to perform fluorescent lifetime measurements on materials such as rhodamine B, rhodamine 6G, and fluorescein. However, replacing the photodiode, with one that a high um bandwidth is began considering to enable measurements of shorter lifetimes, um, such as those mentioned above. For the future work, we plan to replace the current photodiode with a higher bandwidth detector in order to provide the instrumental response and enable the measurement of shorter lifetimes. In addition, reference tests will be carried out with standard fluorophore like rhodamine B and zinc tetraphenylporphyrin, ultimately culminate in experiments on ex vivo biological tissues to validate the applicability of the system in real biomedical scenarios. And that's my reference. And if you have any question, please send into this email. Please visit our Optomechatronics and Energy Laboratory website by scanning the QR code. And thank you for your attention. Goodbye.